When we started taking a look at what architecture we should build using these entanglement distribution focused qubits, there were other codes available and just nobody looking at them. So there's a whole bunch of talent in the world that was working on this space, but nobody was working with them. That's why we're happy to share it so that we can have more people working together to realize this dream for everyone.
Quantum computing needs low overhead error correction to truly scale. Building thousands of qubits to end up with a couple of useful logical ones feels like a bad strategy. Photonic recently published a paper describing a new type of error correction code that promises a 20x reduction in the number of qubits needed to run quantum algorithms. Are these so-called SHYPS codes the path to fault-tolerant systems? Will they help multiple types of quantum chips get there? Find out in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the Chief Quantum Officer at Photonic, Stephanie Simmons. Welcome to the show.
Hey, thanks for having me.
Yeah, it's been a long time coming. We met briefly at Chicago Quantum Exchange, and I've been trying to figure out the best time. But news is always a good time, and your company definitely has some news to share. So we're going to talk a lot about quantum error correction today. So can you give a super brief explanation on what that is, just to orient some listeners?
Oh, absolutely. So error correction is, in some sense, the journey we've all been on or surrounding ourselves with or avoiding over the past 30 years in quantum. So it was known, actually, that you could use quantum mechanics for just amazing things computationally back in the 80s. But for the first 10 years, nobody went to try and build anything because they had no idea how to handle the errors. And this sounds like a really deep technical piece, but it's actually the thing that's going to unlock the entire industry. So it's so important. And I'm really grateful that you and your listeners are taking an interest because it's kind of central to the entire challenge of quantum, right? Like the question of quantum, when is quantum? When is quantum? It's when do you get scalable, application grade logical qubits? That's the only question we need to be answering. How do we get this error correction working, right? So what we're happy to share with the whole world is a whole new way of doing error correction that is way easier and higher performance than what people had assumed was needed. So in some sense, the projections, the long-term projections for quantum have come in a whole bunch, so long as you can use these cool new error correction codes. Would you like me to explain?
That was like the big announcement, right? So on February 11th, which is pretty recent, but this episode will be posting pretty soon after that. You guys announced breakthrough with SHYPS QLDPC codes, and you're going to, I'm sure, explain all that. And up to 20x fewer qubits for error corrections. That's kind of huge. That's a big reduction. Yeah. So feel free to dig in on what that means for the field and how it changes the timeline to get to that, practical quantum computing we were just hinting at.
Oh, yeah, no, absolutely. And it's something that, we didn't know that it was going to work when we went into it either, right? So we're really happy to share this with the world because it hopefully will move everybody to start rowing the boat in the same direction. But why does this matter so much? Well, as I said, back in the mid-90s, they figured out, how, even in principle, how you could do quantum error correction, because you can't use error correction sounds really mundane, right? Like in classical systems, if a bit flips, you usually have a few copies of that bit that you can then just check to see, did one of these go wrong? All right, fine, let's just carry on, right? So there's this kind of easy redundancy that you can put into your system to deal with these errors and just not think about it too much. Quantum can't do that, right? Because we can't copy quantum states. There's these things called the no cloning theorem. It means you can't copy quantum information. So error correction is this whole big deal. It's possible, but the first views on how to make it work are just so extremely consume so many resources and frankly time that it seemed like decades away. And that's why you hear it's still sometimes people saying, oh, these things are decades away, because the resources that you'd need for those kinds of error correction systems is just gargantuan, just off the charts. So it was a major breakthrough a few years ago when they only needed 20 million physical qubits to do something useful. right? Now, remember, we're hearing like in the news, like, oh, wow, we're at like 100 or two, right? So like there's a big gap there. And no wonder people think these things are decades away, right? Because they're like, oh, that's where the goalposts are. And that's where we're at. And that's our pace of progress for the past 10 years. So why on earth would we think we cross those goalposts in any reasonable time? But the answer is those aren't the real goalposts, right? So it was the case, and those error correction codes, those are called the surface codes. You'll see them everywhere, right? If you just Google surface code, it's like hundreds of thousands of hits. Because it has been the de facto standard for quantum. People just assume, oh, that's how you do error correction for quantum. But those are the ones that have the big overheads. And one of the things that we went into this whole business at Photonic, we were taking a look at a whole bunch of assumptions that people had made and just making sure they still made sense for our architecture. And okay, so here's how it gets even more technical, but just bear with me. The reason you use those surface codes is that they're basically provably optimal so long as you work with one assumption, which is that your qubits talk to each other through proximity, nearest neighbors. They just kind of like smush on top of each other, like beside each other. And that's how interactions work. If you take that assumption, basically everything falls out and you have to use these codes. But our technology, we're working from a distributed computing architecture. So we're thinking about a distributed quantum computer day one. We can get into that as and when, if interested. But because of that, we know that proximity doesn't constrain us at all. And in fact, any large scale quantum system that works in that supercomputer regime, where it's a distributed computer over lots of nodes, those won't be constrained to proximity. So what codes should we look at, right? It's not actually given that you'd use the old school codes. And so it was known, and we went into this, a couple of years ago, but it was known, I would say 10 years ago, in the 2010 or so, that better codes existed. You don't need 10,000 physical qubits for one application grade logical qubit. You can have like 100 or like 50. And that's a lot more exciting with the kinds of numbers we have today, right? So, but only if we could crack those codes. If only somebody could figure out how to use those codes in a quantum system, because that required a breakthrough that nobody knew how to do. In fact, lots of people suggested that it might not be possible to do. So what we were happy to share is that, hey, yeah, there's this whole new playing field that we haven't been exploring that make the resource requirements way less, which means actually making commercial value sooner for everybody who can use those codes, right? So that's why we're really excited to share that with the world, because it really does represent a moment where, it might not even be the codes that we introduced in this particular work that end up being the winners. It doesn't matter in so much as, hey, let's start breaking free of those old assumptions, co-design for something that offers value as soon as possible, right? Mm-hmm. And hit the go button together. So that's what we were able to share.
So before we dig into a little bit of how you got there, just one question that might come up to mind for listeners is this work dependent on one specific modality of qubit, only one type of machine, or does it have the chance of affecting multiple?
It's a great question. In some sense, you can invert the question. You could say, hey, for codes this good, right? Because they're not just like smaller. They're not just faster. They have better decoders. They have better, you don't need as many error correction rounds. Like there's all these like other things that make them better. These codes are just so much better in every way that I think it's going to be the case that lots of modalities find a way, right? They engineer a way to use these codes, because otherwise you're stuck with 20 times more cryostats or 20 times more vacuum chambers or 20 times why? Like, of course, you're going to find a way. You're going to engineer. You're going to start doing the co-design for the best codes available, because it's just so central to the quantum stack, right? So I think that's going to be the way that it goes. To answer your question more directly, I do see, just from what I know of all these other modalities, ways that all those other modalities are going to try, right? And I think it's a very reasonable go. Some of them can do it very easily, and some of them might not so easily, but I think they're all going to give it a go.
Okay, so it's not like excluding, really. It's just it might take a little bit of effort for some of them. Yeah.
I think the real critical point is connectivity. And this is, again, it's really interesting because we've learned that same lesson in classical computing, right? Take a look at how the hyperscalers work and all these different workloads. The connectivity and the I/O ends up dictating the performance of the system. And we're finding the same things happening for quantum. So the way that you can connect your qubits up makes you, gives you the ability to apply these codes, right? That's the only major difference. It's like, hey, do you have the connectivity to make this work? Great, then use these better codes, right? And so connectivity, and then the other piece that's going to really come through is the IO. How do you get the quantum IO, which in this case is entanglement, right? How do you get the entanglement where it needs to be? That's the IO bottleneck for many, many, many systems that if you engineer for that, then you're going to do well at scale. So those are the pieces that we're learning, that were learned in the classical system, but I think we're seeing it again play out in the quantum world.
Okay. And of course, the end goal is always the best ratio possible, because you don't want to have a million qubits and then 3 logical ones. That's that's kind of insane.
No, of course, but it's not even just, like, what's the ultimate goal? Like something relevant to people, like commercial value, right? And so that comes about with good cost of goods, right? You have to think about reasonable cost of goods and how much does it take to run one of these things from an energy perspective, from a capital expenditure perspective, but you also have to deliver something in a reasonable amount of time. Right. So it is the full package, right? It's like, how is something valuable? How does it have utility? It's not, yes, size is absolutely one of those things, but it's the full package and we have to be designing for all of it.
So you've been working on this for a while and your team. This is a long problem, like it's decades long, I guess you could say, as a challenge. So what key insight all of a sudden got Photonic to kind of crack this problem now?
Right. No, I think it was serendipity a little bit. So, no, it was. So truthfully, it is still very much a 0 to 1 space. Like people feel like it's old and you feel like it's decades old and these modalities are kind of locked in. And I think that actually is a little bit too soon, because there's a lot of innovation happening within each modality. And frankly, you could even decide to call it a different modality with how many changes are coming through at the very, very basic level. It was the case 10 years ago or so. So our company, Photonic, has actually only hit the go button, let's say in 2021. So we're relatively young, right? So we've done all this since 2021. Our qubits we went hunting for them. I went hunting for them about a decade ago because I was looking for something that it was best for entanglement distribution, and we can get back to that. But when we started taking a look at what architecture we should build using these entanglement distribution focused qubits, there were these other codes that were available and just nobody was looking at them. Like there's these old academic papers that say, oh, even though these codes are not, you can't implement them in nature, it's still an interesting academic exercise to go and explore what they like. So people had no clue that these things could even be achieved because they weren't thinking that connectivity with quantum was possible. Like there's just really deep belief that proximity is how you get this thing to work. And if you relax that and you do an entanglement first piece, then all those assumptions kind of fall away and you have other upsides. And so fortunately, the reason we were able to make progress on this is because honestly, maybe it was just a bit of hubris, but I went into this and I looked around at all the different codes out there and I said, okay, well, let's go and see if we can make these ones work. Because if it pays off, then, outstanding. We can take the timelines in by a huge amount. And if not, then we just use the surface code like everybody else. So there's a whole bunch of talent in the world that was working on this space, but nobody was working with them. So we kind of brought them all together and put, great, smart people doing smart things, and kind of magic happened. But it needed that little push to kind of start the snowball. And that's why we're happy to share it with the world so that we can have more people working together to realize this dream for everyone.
So everyone should be working towards using these codes in their qubits. Tell us a little bit about your qubits.
Sure.
And how they differ, your modality.
Oh, thank you. Yeah, happy to. It's been a journey. So I came up through the ranks, right? I've been in this space since 2001 and took a look at all the different modalities out there and what they were working on. And many of the options out there weren't really thinking about the full scale distributed system, in my view. From the outset, everybody was still working on getting the basic components to a degree of functionality, and rightly so. That was kind of how the approach was in academia. But once you start working on this from a company perspective or a commercial perspective, where you're really trying to deliver something useful to people as soon as possible, and you make the assumption that you need error correction to do that, then you kind of take a different systems engineering approach and you think about the feasibility of distributed quantum computing. So what do I mean by distributed quantum computing? I just mean taking some number of quantum bits, ideally more than one, ideally a large number of quantum bits that can work together over a network, right? Because when you think about scale, even if you could work with these amazing codes, you still need lots of qubits, and you would still benefit by having more qubits than you need because you can always make space-time trade-offs to make things go faster. So you're going to want lots of resources, just like classical computing. You want the resources. It makes everything better, right? So having that kind of scalability baked into the way you think about things matters a great deal. And the challenge to almost every quantum architecture out there, by virtue of being based on proximity, right, literally smushing qubits on top of one another, it means it's really, really, really hard to get clean quantum signals out of the box, whatever box they're in. Right? All of these systems are in some box because they need to have environment controls. So it's either ultra high vacuum or some chip in a cryostat or whatever, like it's some box. And they're all limiting, like in some sense, that you can kind of get them bigger, but that becomes harder and harder and R&D and engineering to make these boxes bigger. It's way easier if you can take different nodes and just link them together, if your physics allows for that. So it really does matter, like what physics you're working with. And so I went hunting as a professor 10 years ago. I went hunting for what I thought was the kind of unlock for that kind of scalability piece. So we knew that silicon spin qubits were amazing. Spins just in general are amazing. But what was needed was that telecom link. Like, how can we get a really, really good matter-based qubit to send out a photon? Because photons are great at room temperature and they can link across data centers and whatever, especially telecom ones. You don't need to rewire anything. You don't need to do any transduction or loss. Everything's really low loss. You can have it work well. So I went hunting, and I honestly, I thought it was going to take like 30 years to find the thing that was going to work. But we found it in a couple of years, and that's when we hit the go button from a commercial perspective to do this. So what we work on is called the T-center. It is a small molecule trapped in silicon, very reproducible. It forms naturally if you have the constituent atoms around, and it sends out telecom light, and it spits out telecom photons, single telecom photons that can be entangled with the spins that are left behind directly. So this is like phenomenal for density. You could put we've printed 1 million on a chip. The controls are much, much more challenging than the qubits, to be honest. So we're scaling the controls now, but the qubits themselves you can print at scale, and they can link out via telecom light, and we've already gotten multiple quantum cores working together in a distributed quantum computer in just kind of a basic form. And it's getting better every month, right? These spin qubits are phenomenal, and we can iterate quickly because it's silicon and it's telecom. So it kind of has that engineering. It's got a lot of competitive advantages that allow us to move as quickly as we have, right? Again, these are very young qubits. We only shared them first with the world. They're like 5 years old, these qubits, right? So really new, but it's based on a lot of old physics, high quality spins, same physics that allowed us to set 3-hour coherence time records back a decade or so ago. Spins in silicon are amazing. Just what's different about these is that you can get them out of the box and scale horizontally. So that's our basic technology. And we're really excited to be moving as quickly as we are with it.
That sounds great. And anyone who's listened to a lot of different modalities and designs, they've already heard some key things in what you said. This idea that you've already got little boxes talking to each other to build a bigger box, which is, that's sort of the dream for everyone right now, really, just to keep scaling up. So we're going to want to dig a little bit on that, and I'm going to try and put you on the spot and get some numbers out of you, maybe just some sense of scale and where we're going. Sure. But before we do that, just to keep it real, what would be a real world application that could benefit from this like reduced overhead that you're pushing for right now with these error correcting codes?
Yeah, every single one of them. Just to be a little bit flippant. No, but okay. So it wasn't clear, right? When people went into commercial quantum about 10 years ago, and people started trying to use these noisy intermediate scale quantum systems, it was not known, and even earlier than that, like the earlier like annealers and the rest of it, it wasn't known if there was commercial value there. However, it was known that they could access computational space that could not be accessed by classical systems in principle. right?
Mhm.
So it was totally valid to go and try and see what kind of heuristics might emerge to deliver good ROI, right, without error correction. I'm fully in support of. I was really, happy to see that early work come through, because had there been a heuristic that emerged, like a heuristic is an algorithm that doesn't have a deterministic answer, but just seems to work, right? So like optimization things fall into that category. Even AI to some level fits into this category. They just at a certain scale seem to work. Now, because it doesn't have that like solid complexity theory backing to it all the time, it was worth the adventure to go see. My tack was always to go and, I was young coming into this space, right? Like I fell in love with quantum when I was 16. I wanted the full career here. So I knew that I had to play the game where we had to think about the big, large scale error corrected system. And that's where I spent my cycles. But every other application that we know of that has commercial value is all in this error corrected space. And so every single application that you think of, including actually even the heuristics that may click in, right? So there are quantum heuristics that might actually start showing value once you can rely upon the systems, once they're error corrected, right? So the entire world of quantum opportunity, as it were, that relies upon error correction benefits from these codes, so long as you can use them. And that's why we're really excited to share them with the quantum world and beyond.
Okay, I didn't know if there was some like pet use case that you always are pushing or something.
Oh, I mean, there's stuff that gets me up in the morning, but I think the whole point is that this is an industry and we're not going to be able, it's going to be used on a platform basis on so many different things. So any typical application you hear can be applied in a universal system. I think that's the point.
So back to your vision of a networked quantum computing world, right? Yeah. And we're not going to deep dive into just networking in general, because if you ask 10 people about quantum networking, you'll get 100 different answers, right? So we're not going to go too deep on what a quantum internet is one day, but
I'd be happy to. But you're right. There's lots of different. There's lots of
there's a lot of different views of what people want to use it for. But for now, just the idea of putting these systems together to act as one. How close are we to seeing this deployed at scale? What challenges remain in linking and getting these to work as a system that you could just log in, cloud access, and hey, all of a sudden I've got 4,000 qubits or something. Right? How's that like roadmap looking?
I can absolutely speak to the broad ambition, because in some sense, when you're asking about that roadmap, you're asking about almost all the quantum roadmaps out there now, right? Mm-hmm. I think it was really interesting because about 10 years ago, everybody was just like, they only cared about T2 times and fidelities. And that's the only thing they talked about. And now it really is like, okay, we have to recognize that one perfect qubit is perfectly useless, right? Like the only reason we have value is when you can link in something like 400 to 2,000 logical grade or application grade logical qubits, right? That's where the money is. We know that it might be that there's something that comes in earlier, but we know that that's where there's going to be a lot of value for everyone. So how do you get that when each one of the boxes out there really do constrain your system? Like there's some approaches out there that hope to hit, something like 1 million or so on one box. That is going to be many, many R&D cycles to do that. That's what like. You can say the same thing for classical computing. It's taken decades to get the number of transistors onto one chip up. Mm-hmm. But you could see even earlier that networking many smaller systems together delivers that kind of value quickly, so long as you can hit those performance numbers, right? So for us, we've already done distributed computing. It needs to go faster. We need it to go faster, but the physics of the solid state solution that we have does allow it to go as fast as we need it to in principle. That's why we're really happy with it, is that, the first models, again, these are 5-year-old qubits. So just making sure that there's no unknown unknowns as you're going through is really important. And we don't see any so far. It seems to be all fitting the models. But we need to go faster. And if that's enough, then we can go fast enough to use these codes. And then honestly, we have all the pieces already lined up because we have this entanglement distribution piece. I would say that if you go and you take a look at the actual, what's called the quantum resource estimation, or like what it takes to build a working quantum system at scale with the right kind of resources, most teams, if not almost all teams, completely ignore the costs of the IO, the quantum IO. Mm-hmm. And this is really, it's the cost of entanglement, getting entanglement to a good degree across many systems. if this is a hidden cost, which is actually the dominant cost in many, many systems. So unless you're engineering for that, it's going to be a lot like classical systems. Unless you're engineering for really solid connectivity and IO at scale, those systems won't perform well enough to deliver value.
Okay. So not speaking for the whole industry in general, just would you have a guess as to when we'll see X number of logical qubits from Photonic? Or
it's definitely years, not decades. Although you do have others that are saying similar things. It's going very quickly, but we're not going to put dates out just yet. But it's very encouraging. Let's say.
Yeah, the years, not decades thing. You said a couple of things, and million on one chip. Yeah, we all know something that literally was just said days ago about that. It was in fact, our last episode was that. Yeah,
but truthfully, and they've done a great job working on thinking about what it does from a systems engineering perspective. Like, if you don't network a system and you want to do a full scale up solution, you have to think carefully about that, and they have been. So scaling the controls is a really, really big deal. So I don't want to take that million qubit chip out of context. That's a manufacturability and like quality assurance kind of piece for us. The controls is a massive piece of this puzzle, right? Not just getting the entanglement where it needs to be and the yields up and the rest of it. This is like a beautiful, beautiful multi-dimensional engineering challenge where you need to benefit from everything you can, including, yes, way better error correcting codes. If that can take the cryostat count down by a factor of 20, I'll take it.
Absolutely. Yeah. And you've already mentioned that silicon is a big part of your design. And how do you take advantage of that? What kind of edge do you see that giving you? Because obviously we are a silicon world, right? We've been building for this technology for a long time. It's not that new. It's just that now they're qubits too. But
that's exactly it. And in some sense, we get to benefit from it in two ways, because what you might not appreciate is that it's actually, frankly, the best quantum material out there too. Partly to do with the fact that we've purified it to death, right? We know how to make super, super, super clean silicon for the semiconductor industry. But it is the case that because it's a group 4 element, it has really low magnetic noise environment. There's all these like physics pieces that make it a very, very excellent environment for spin qubits. And we've known that for a while. But what I think it's not just the quantum performance, which of course you need to hit, but it is the dominant silicon, it is the dominant photonics platform. So the name of the company is Photonic, and we named it that way because really that's the most non-negotiable glue of a distributed networked quantum computer, right? At some point, you're going to hit the limits of your box and want more, right? And you're going to want to network these things together. And if you just take that as a given, then there's no option really from a commercial sense other than photons. Like that is the glue that puts it all together. But what we can offer in the silicon is really high density and high quality storage of information, right? As I shared previously, we have, we've demonstrated 3-hour coherence times for spins in silicon. Like these things are, and really many, many nines and all the rest of it. Like these things are really, really solid. It's kind of like a trapped ion in a solid, right? It's one term you can think of as like a semiconductor vacuum. Like these things are trapped there. So because of that, you can manufacture really quickly. We turn around chips really quickly, and we have independent manufacturing chains. We know how to work with silicon, but it is essentially how you print fiber optics on a chip, right? Is using silicon photonics. So you really do want to have that baked into your system, not just telecom. We put our qubits right into essentially those printed fiber optics on the chip. So you collect all of that light and you don't need to worry about recooling or anything. You can kick it really hard. There's all these little competitive advantages that make a difference. So yeah, we're really happy with how well it's moving.
So would you say there's some kind of still like a little bit of an advantage tied to your platform around these codes? And if also in addition, do you think this is going to create some kind of like arms race now? It's like, no, we're going to use those codes better and show Photonic. I don't know.
Hey, I think there's it's going to be a very dynamic next couple of years. Absolutely. It's going to be a very dynamic next couple of years. And honestly, the sooner we can, as a community, demonstrate commercial value, the more the rising tide lifts all boats. So I see no harm in, hey, if we can go and show a killer app, I think we'll be able to hit there first. But if there's something else that comes out first, that's still good for the industry. And if it uses these codes, excellent. What we do know is in the long term, a solid state solution to this kind of engineering challenge looks very, very good, right? And so long as nothing, there's no unknowns that creep in, these things do look like they can have the metrics needed to really deliver something useful at scale at a great price point. So that's what we're really just heads down on execution at the moment. And if there's other things that come in to accelerate things, then so much the better.
So as Chief Quantum Officer, which is a pretty awesome sounding title, right? I mean, it's a title that wouldn't have even existed a while ago. It's pretty sweet.
Yeah, I took that one 2016.
Yeah, that's pretty cool. What's your biggest priority right now for your company?
Execution. Okay. Execution. You have to, get your head down and focus. I think we know where there's a lot of work in the industry about where these commercial advantages and where these exponential speed ups in commercial applications exist. We know what performance metrics are going to need to hit to deliver them. Everybody inside is very motivated. Yeah, no, it really is just about making sure that we move quickly because as we've shared previously, so all these modalities, they have like 30 years under their belt. Do you know, they have so many academic researchers around the world that have, buckets and buckets of work that's contributing to that effort so that they don't need to do that work in-house. So we have to be extremely smart and make really smart choices every single day so that we can compete, right? And ultimately deliver value soonest. So it's all about execution. And sorry, that's a bit of a boring answer, but that is what we get up in the morning and think about.
No, but it does lead me up to a question that I'll probably leave us with here. What would you think is the next big breakthrough that you're aiming for then in this execution path? Is there some next milestone that once you hit that, you're like, whoa, yeah, this is the next thing that SHYPS is helping and other.
Yeah. What we really like about this platform is that we've kind of proven out all the basics, right? A lot of the systems that have to go back and network their systems honestly have to go back to the drawing board in a very, very fundamental sense, because the amount of entanglement that you need is a lot if you want to do anything useful at a reasonable rate. So you have to really redesign almost like the basic functionality of your qubit. We don't have to do that. We've already gotten distributed quantum computing working. We just need it to go faster. And, people know how to iterate and improve. So we're heads down on iterating and improving, but we don't need to kind of go back to the drawing board at any point to add functionality. That core functionality has all been proven out. So we need to get it to the point where it's fast enough to do, high-grade logical qubits, right, on a distributed computer. I think that's really the unlock, because at that point, if you can get distributed logical qubits, then it only is a matter of money. Do you know what I mean? Like then you can just go and start imagining building out larger scale systems that deliver the value needed for commercial applications. And you could think about working on costs and the rest. But we don't need to redo any physics or learn anything new. So everything that we're doing is all about heads down on executing to that goal. So
it sounds like there's a whole lot of interconnect secret research going on at Photonic right now, right?
Okay, so this is a really good point. Even the term interconnect presupposes a certain way of looking at things, right? You imagine, like even just classically, you think, hey, okay, we have, a computer and then we just stick on like some transduction thing or some NIC card, right, to get the signal out. But that's actually not the way. Like if you want to do logical operations between high efficiency quantum error correction blocks, you almost need every single qubit just about talking to its copy. Like you need a huge amount of entanglement to make that not be the rate limiting step for your system. There's caveats and asterisks around that, but basically the more you have, the better. And even when you do clever compiling. So even the term interconnect presupposes that you take something and then you change it into something else. For us, it's really in the qubit itself. Like we have what's called a spin photon interface, and that's true for ions are similar. But any solid state color centers are like this. They talk to photons as well as they store their information in their spins. Like it's one object that has both interfaces, as it were. They can talk to both degrees of freedom just as well. So I think that's really important, is because it's not just about interconnect. It really is like, oh, hey, let's work backwards from success. What does it need? What do you need to deliver a large scale distributed quantum computer? You actually need this baked right into the core of what you do. And then that scale can come naturally.
Yeah, it sounds great. I can see a pathway forward in turning your execution into something practical in the world with that approach, for sure. It sounds like you're building right from the ground up. So lots of luck. And I hope to have you on before we know it to share some some systems we're accessing on the cloud and benefiting from.
Absolutely. Thank you. Thank you so much for your interest.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Photonic wants to slash qubit overheads and reimagine how quantum systems connect. We all know quantum computers are fragile and error-prone. For decades, the field's been wrestling with how to tame those errors. Error correction isn't just a technical footnote, it's the key to unlocking quantum's full potential. Old-school surface codes demanded thousands of physical qubits just to produce one reliable logical qubit. A few years back, estimates pegged 20 million physical qubits for anything useful. With labs boasting just 100 or so physical qubits today, it's no wonder skeptics pegged quantum as decades away. But Photonic unveiled quantum low-density parity check QLDPC codes that slashed the qubit requirement by up to 20 times. Think 50 to 100 physical qubits per logical one with these new SHYPS codes. Surface codes thrived on the idea that qubits only talk to their nearest neighbors, but Photonic's betting on a distributed quantum architecture where connectivity isn't bound by proximity. This opened the door to dusting off decade-old academic papers on better codes no one thought would work in practice. Photonic's spin qubits are tiny molecules trapped in silicon, spitting out telecom wavelength photons that can zip through fiber optics. They've printed 1 million of these on a chip and are working on controlling them at scale. The path forward relies on distributed quantum computing, linking nodes across rooms or data centers, and Photonic already demonstrated entanglement over a network. Photonic's SHYPS QLDPC codes thrive on this type of connectivity. Stephanie expects other modalities to try and adapt to take advantage of the codes too. Photonic is focused on an approach of iterate, accelerate, and execute in this march towards fault tolerance. The goal is commercial value, delivering something useful at a sane cost and timeline. They're racing to get distributed logical qubits online in years, not decades. That does it for this episode. Thanks to Stephanie Simmons for joining to discuss Photonic's work in error correction. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.